Hi, welcome to the fifth and final class for Python for lab work. Today we're going to be covering Biopython, and what Biopython is a set of Python tools that are designed to handle molecular biology computational data. So I have two links here. The first one is the overall page for Biopython. Biopython has a lot to actually offer. I'm not going to cover everything here. I'm just going to cover some of the uh, more useful ones that are immediately useful. But you can look in here and see like, oh, it can do all this type of stuff. So if you want to do these things, they're here. And also as a nice introduction and explains like how things work. So let's get into it, and let's do our first module from Biopython, which is seeks. So Biopython seeks. Sequences, nucleotide sequences, are their own type of objects like list or strings. Sequencing can be analyzed in certain ways. To get started, you have to import. Let's just clear this. You have to import biosequence. So import that. And now what we're going to do is that we want to turn this string, this AGTACGG nucleotide sequence, which is a string as written, into a sequence piece of data. And the way that you do that is that you put this sequence function around it. So let's run that. And now let's run and we're assigning it to my sequence. And when we run my sequence, it gives us this sequence, and then it gives us the nucleotide sequence. And if you want to like have it without this sequence here, you just print it and it comes out like that. My sequence dot complete complement. So there are various things that the sequence can do. So we have this sequence that we created, and then what we can do, let me just, you go my sequence, whatever sequence you, and then you have all these options. You put a dot next to it, and you have all these options you can do with it. So you can look through here and see if anything of interest is there. All right, but first off, we're going to do my sequence complement, which gives you the complement to the sequence. So you can see here, you got T, C, A, T, G, C, A, C, C, A, which is a complement to the original sequence. There's another function called reverse complement. I run that, and it gives you the reverse complement. This is the complement again, just reversed. And then we have mySeqs dot translate, and it does what you think it does. It translates it. And it gives us STL because that is the sequence that is the protein that this sequence would produce. It's giving me this warning sign because this sequence is 1, 6. It has too many. It has like 2 leftover nucleotides, so that's why it's giving me a warning signal because it's not in a reading it's not in a perfect reading frame. All right, now let's do my sequence complete mRNA, and it gives you the mRNA of the sequence, of the complementary sequence. It would be produced by that. And then you can use the find function. And for this example, we're going to find AC, so these 2 nucleotides together, in the sequence. And you can see it tells us it's in the 3rd position, which means it's actually in the 4th position because of the Python 0 indexing. So you can see here it's 1, 1, 1, 2, 3, 4. So it's right there. Sequences can be indexed like strings. We talked about this in the first class. So if you want to get the first variable of the sequence, you just put 0 for the first one. It gives us A because that's the first letter in the sequence, the first nucleotide. Or you can do negative indexing, which will -1 will give you the last nucleotide, which is T. Or you can do slices, where you can slice a portion off, so 1 to 3 gives us GT, which is here. And then you can do steps, so you can get every third or whatever. So it's start, stop, step. So it's going to start at the beginning. It's not going to have a defined end, so this end when it reaches the end, and then it's going to have 3 steps. You can see it goes 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, AACG. Something else you can do is you can get a count. So you can count how much of a certain sequence or a single nucleotide is in the sequence. So that is my sequence dot count. And we can press this and then hit that. And there's only one in here, which is this one. Only 1, 2 GG. And it's right here. But for example, you want to get the GC content percentage manually from the sequence, you can do this mathematical equation. So you just use the count to count both the G and the C in the sequence, and then divide that by the length of the sequence, so how many nucleotides are actually in the sequence overall, and times that by 100. And it gives you a very long number of 45.45. All right, now we're going to, but then there is another way to do it that's actually built in to actually get the GC count. And it's, you have to get it, you have to use from bio.sequence unit tells import GC fraction. And we're going to run it. And you can see it gives it the same fraction, but we didn't times it by 100. So it's in a decimal point, not a percentage, which this one is. So that's one way to use this. So you can also combine sequences, concatenate them. So what we're going to do is that we're going to assign sequence 1 this sequence. And then we're also going to assign this sequence. We're going to assign sequence 2 to this sequence. And finally, we're going to put them together. So sequence 1 plus sequence 2. And it gives us this combined sequence down here. And usually you would assign it. So let's assign it. Sequence 3 equals blank. So let's run it. And then you can see now sequence 3 is the combined of sequence 1 and 2. There's another way to do this, and it's you can join sequences together. So we're going to make a list of sequences and call it contigs. And then we're going to create a spacer. And then and then we're going to use spacer as a function. Spacer dot join, and then put contigs to list. And you can see it is joining all the sequences together, but with the spacer in between them. If we don't want that to occur, we can just get rid of the spacer. Is assign the spacer to essentially nothing. Nothing. Run this again. Run this again. Oop, doesn't want to do it. Never mind, I guess you cannot do that. You could. Anyway. So now another important thing when you're analyzing sequencing data is sometimes the data capitalization is wrong, and since Python is so case sensitive, so if you have like for example a sequence that has partial um, capitalized and uncapitalized, that actually can mess it up because it will treat lowercase a and capital A differently, or you'll get a mixed set of data where some of it's capitalized and some of it isn't. So to make sure that everything is like the same, you need to capitalize it or uncapitalize it. You just need to make it uniform. So, and this is what changing case is. So let's get the DNA sequence, and then let's look at it. You can see that it is not the same case across the whole thing. Now let's run DNA sequence upper. You can see now it's all upper, or we can do DNA case dot lower, and now it's all lower. This does not actually change the original sequence. You can see here is it the same sequence, so you actually need to assign this a new sequence. So doing this upper or lower doesn't actually change the original data. It just like how do put it? It just changes it here locally, but doesn't change it like the actual like first this initial one. So you have to assign it. All right, now let's get into Biopython files. From bio, import sequence IO is the first thing you need to do. And then import OS as well. So these two are what you use to handle the data. And then we have to set the working directory where the file is at. So os.change directory. And then we're going to open the FASTA file of various orchid species shared mRNA. So basically, we're going to, or there's a file I have here. I can get to it. And it has the various the same gene, though the various orchid species of a shared species is a flower, and this is like a gene that they all have, the various species of this type of flower, and then you can just look at, and it's just a big old vast list of it. So get the current working directory going. I already did that, and then we're going to get the orchid data out. So ls orchid.faspa, as you can see here. And we're going to assign the data type. This needs to extract as FASTA. So it's sequence.io and sequence, and then it's going to parse this file, treating it as a FASTA file. And since there's multiple sequences in there, I'm running it as like a loop that will go look through all of them individually. And while it's looking through them, it will get the ID off of the sequence, the record of the sequence, and then the length. So let's run this. scroll all the way up to the top, and you can see here it's showing us the information for the first one, 658. The information about it. It then gives us an abbreviated version of the sequence because it's too much for it to print. And then it's giving us the length of the sequence. So this is giving us all the information about the sequence. And then it just continues on because there's so many sequences. It just continues giving little summaries of the sequence. And this is not the only thing you can do with this. Is just an example of how we can handle the information and how we can extract various parts of the sequence data out of the FASTA file. Actually, the homework assignment actually revolves around using this in different ways, so I'm saving that for the homework. Instead of using a loop like we just did to do this, we can use the next function on an iterator to stop through the entire list like this. So once again, you go into bioimport and get sequence.io if you haven't done it already. And then records iterated. So we're going to once again parse, use sequence.io dot parse to get this ORCID file and then parse it as a FASTA file. Okay, so now we see that now we have this record iterator here, and we're going to put it inside the next function, but we'll look at the first record. So you use this next function to first look at the first record. So let's run that. All right, and now we're going to print the first record's ID and the first record's description. Once again, it gives the record of the first. This is the first one. And let's get the description. And it gives this information as well. Like the full information. So that's one way to parse, look through the data of a FASTA file. And then you can also extract the sequence. So you're getting the sequence out of the first by doing first record, which we assigned here, and then dot sequence. So this is it, and then you assign it to a variable. Run it, and then it gives us the sequence down here, which is rather long. It's like 700. And then you can do and then you can just move down. So like then when you hit next again, it just goes down to the next record. So this is the first one, and this would be the second one. This could be very tedious if like it's a long list like this one, if you just do this over and over again. But there are other sequences that are like smaller lists, so it just would be more feasible, or just maybe even just one. So now we're going to do the second record. It's same as the second as the first. So you gotta make sure you do the first before you do the second. With ID, and you can see it is this ID right here. You get the description, and this description. So move down from this one to this one when you use the next function again. So this one, the first next, we'll look at the first one. The second next, we'll look at the second one. And if we kept on doing this, like a third next or a fourth next, they would look at they would refer to the corresponding sequence inside the FASTA file. All right, and now we're going to do basically the same thing as we did up here with the FASTA file, but with GeneBank instead. So for sequence record in sepio parse sequence.io parse, and you get the file, but now it's a GeneBank version, and then you set the type of file of GeneBank. Run this. Whoops, sorry. Run the whole thing, and you can see is parsed from the GeneBank file, and I should show you the GeneBank file. Give me a second. This is the GeneBank file. It doesn't really. Let me try to open it in this. You can see here is the GBank file, the GeneBank file, and you can see how like the FAFSA is like pretty clean, but like looking at this, it's like a very useful to like use Python to actually like organize this, so you don't have to like do this manually of like copying this and separating this from the separating the numbers from the numbers and like what is what. So this would actually save you a lot of time if you had to extract all the data out of a GeneBank file. Because just look at it, it's so much information, but none of it, not everything is useful. Like author, good to have in there. You don't really need that for your analysis. All right. In the previous section, we talked about the fact that bio.sequence.io parse gives a sequence record iterator and that you get the record one by one. Very often you need to be able to access the record in any order. The Python list data type is perfect for this, and we can turn the record iterator into a listed sequence records objects using the built-in Python function list, like so. So we're going to create a list of pieces of data. So once again, we're going to get the bio import sequence IO. And then we're going to assign the record this. We're doing the parse again, but we're going to turn it into a list. And then we're going to print that list. And now you got all this information in one big list, which can make it easier to handle because it's all in one place. And then if you want to see the first record in this list, you do record 0 because Python is 0 indexed. You hit that. And then let's print out the first record ID, and it gives us it for the sequence at a length. And so this gives you a really easy way to handle and look through the data. So today is pretty short, and the reason why is that this is a lot to learn, and it's a bit of a deep plunge. So I didn't want to overwhelm everybody. And also I wanted some time to talk about the homework, because this is a more difficult form of the homework. So let's go look at the homework. So it's pretty, on itself is pretty simple. Let's take this file that we've been working with in this session and just transcribe and translate all the sequence in them. And so that is basically using this function here, part of it at least, and then using some of these up here. So that's the homework. Thank you for taking the Python for lab work, and I hope this has ignite your curiosity about Python and how to use it in lab work and analyzing data. Please, if you have any other questions about the homework or any questions about Python, how to use it, please don't hesitate to message me via my email. Thank you, and goodbye.